Hi, in this video we're going to look at the intersection of these two things. And so it doesn't say here in the problem what these two things are, but at this point you should be starting to recognize these equations and the different forms of the equations for the things that we've been working with. So this first one here is clearly in the form of the equation of a plane, ax plus by plus cz equals d, right? So that's standard form for an equation of a plane. This is a plane. This other equation over here, maybe at first you don't recognize it as the equation of a plane, but if not, then you maybe do a little rearranging of some terms and you recognize that this is also the equation of a plane. I'm going to add or subtract some terms from both sides of the equation to get it in this standard form. So I'm just going to subtract y from both sides of the equation. So I'll have 0 equals 2x minus y plus z. So all I've done here is rearrange that equation so it's in a form maybe we're a little bit more familiar with for the equation of a plane. So what we're looking at here then for this example is finding an intersection of two planes. All right, so before we dig into actually calculating the intersection of those two planes, I want to think a little bit about the geometry of that. So if you just think about two different planes that are in space here, so I've got some kind of just pieces of cardboard to use to kind of visualize it. There are really three possibilities for how those planes could be oriented with respect to each other in space. So one is that they would be the same plane, right? So two equations of planes that are the same plane. These two are not the same plane. So we can show that by showing that these two are not the same equation. Right, so if I look at the equation here and think about trying to manipulate it, so for example, I've got a 2y for my y coefficient, you can see that you're not going to get the same equation here that you would have here. So these are not the same plane. Another possibility would be that the two planes are parallel to each other. So if you think about the ceiling, if you have a flat ceiling, the ceiling and the floor, those would be two planes that are parallel to each other. So in that case, they would not intersect. And then the other possibility is if they're not the same, and if they are not parallel to each other, so think about them being tipped a little bit, thinking about how they would intersect. And just to kind of help visualize, thinking about that, so if you think about two planes intersecting, however they might be intersecting in space, sort of like two pages of a book or a folder or something like that, you can think about that they would intersect along a line where those two planes intersect. So if these were planes, they would extend beyond my little piece of cardboard here, but their intersection would be a line, not a point. You couldn't have two planes that just intersected a single point. Okay, so if we're interested in the intersection of these two planes, we should first of all verify that they are not the same plane. Putting the equations in that same form should make that obvious, that these are not the same plane. So I'm just going to write some little notes over here. So these are not the same plane. If they were, they would intersect at every point that's on both planes. I can also verify that these two planes are not parallel to each other. If you think about the geometry of two planes that are parallel to each other, and think about the things that we can get from these two equations, if the two planes were parallel to each other, they would have perpendicular vectors, normal vectors, that are in the same direction or the exact opposite direction. So if you think about two planes parallel to each other and think about a vector that's perpendicular to them, you can see that that vector perpendicular to one would also be perpendicular to the other. Perhaps in the opposite direction, but exact opposite direction, and perhaps different magnitudes. So if you think about normal vectors for each of these planes, this plane, it's easy to get a normal vector from taking those coefficients of the variable terms when it's in this standard form. So a normal vector to this plane would be 1, 2, negative 4. And a normal vector to this plane would be 2, negative 1, 1. Again, when we talk about normal vector here, we're really talking about a direction. I don't care so much about magnitude. So if these two vectors were going in the same direction, they would be scalar multiples of each other. It's pretty clear from looking at them that they are not scalar multiples of one another. I can't multiply this first vector by a scalar. So I would be distributing that same scalar to every component there and get this vector here. So these are not scalar multiples of each other. So these two planes are not parallel. So both of those things I decided really just from kind of paying attention to the equation here. There's not a lot of work to write out for that. I did write down a couple vectors, but you can see that you would be able to just look at these coefficients here and think about that vector without needing to write out work to justify that they're not the same plane and not parallel planes. All right, so that means that they do intersect along a line. So when we think about how I might write my answer for a problem like this and think about that line, remembering that when we write equations of lines in R3, we need two things, a point along the line, a point on the line, and a vector along the line. And we're going to have parametric equations involving t for that line. Okay, so just kind of keeping an eye on what we want our answer to be here for this. Okay, so there are several ways to do this. The textbook that we're currently using, I'm not crazy about the way that they do these problems. It's okay, but I think it's kind of unnecessarily complicated in thinking about that. So I want to talk about a slightly different way than the textbook does. Anytime we're thinking about an intersection of any equations or surfaces or points or lines or whatever we're thinking about in R3, we're really talking about finding values that make both equations true. I'm just going to go back and use the two equations that we were given to start with, although for this second one I could really use either form, what I was given to start with or when I rearrange that. And so when I'm thinking about the intersection here, really what I'm looking at is solving a system of equations. I'm looking for the x, y, z values that make both of these equations true. So I'm really looking at solving a system of equations. I have two equations and three variables, x, y, and z. So that's an underdetermined system, which means that you can't just find a single ordered triple, x, y, z, that satisfies that, which we should expect. We are looking for a line here. Remember that our line is going to involve a parameter t. And so we can exploit that kind of as we go through the algebra of solving this system. So there are a lot of different ways to solve systems of equations. For this particular problem, the way these two are set up, I might use substitution to solve this system. This second equation here is solved for y. And so if I just substitute that 2x plus z into the first equation in place of y, I'm working towards solving this system. Okay, so I'm going to have, when I substitute the second equation into this first equation in place of y, x plus 2 times the quantity 2x plus z minus 4z equals 12. I've got some like terms I can go ahead and combine here, so let's just go ahead and rearrange that. So here I'll have an x plus a 4x, so 5x. And then for z terms, I'll have a plus 2z minus 4z, so minus 2z equals 12. Okay, so that's what I get when I combine what these two equations have told me. And depending on the algebra that you choose to do, what you get might look a little bit different here. But they both should represent what's happening for both of these equations, what makes both of these equations true. When I solve this system, because I have an underdetermined system, and I will have infinitely many solutions to this system, I will have what we call a free variable. So you might remember that from algebra when you worked on solving systems of equations, a free variable. And we often use a parameter to represent that. I'm going to use t, which is what we often use for parameters in our parametric equations. But you could use something else too, a or something else, just maybe not x, y, z, since we have those representing something else. So at this point, I'm just going to choose one of my variables, x or z, to be that free variable t. I'm going to choose to let x be my free variable t, but it could be either one here. So I'm going to let x be t. That's going to be my parametric equation over here for x. x equals t. And once I do that, then if I substitute x equals t in here, then I can solve for z. So I'll have 5x minus, I'm substituting in for t, t for x, so let me just fix that. 5t minus 2z equals 12, and then solve for z. So I'm going to add 2z to both sides and subtract 12 from both sides and then divide through by 2. So that's a couple different steps of algebra there, but I will have 5t minus 12 all over 2 when I do that. So there's my z equation. I'm going to tidy that up a little bit and maybe write that in the form we're kind of used to seeing for parametric equations. So I'll make that 5/2 t minus 6. Okay, so now all that's left is to find my parametric equations for y. And I have x in terms of t. I have z in terms of t. And now what I need is y in terms of t. Again, we're really just algebraically solving a system of equations. So I could go any place that I have x's, y's, and z's here and use this information to get my y. Probably the easiest place for this problem is the second equation we were given. Right? If I put in for x what I have for x, and I put in for z what I have for z, either this version or this simplified version over here, I'll get my equation for y. Okay, so I'll just do that work right here. I'll have y equals 2x, so 2t, plus my z, 5/2 t minus 6. Combine these like terms, and then I can write my answer over here. So 2t plus 5/2 t is 9/2 t. Okay, so that is one set of parametric equations for the line of intersection between these two planes. As a way to verify that that really is true, you might kind of think about what this set of parametric equations represents. The constant terms here, 0, -6, and -6, represent a point on this line. So that point would need to be on both planes. You can verify that the point 0, -6, -6 is on both planes by verifying that that makes both of those equations true. It is. And then the coefficients of the t here, those would be components of a vector along the line. And so you would want to make sure that that vector is along the line of intersection between those two planes. You can verify that as well. With that being said, too, notice that if I think about that vector along the line, 1, 9/2, 5/2, I'm really just interested in that as a vector along the line. I'm really interested in a direction, not necessarily a magnitude. So any scalar multiple of this, any non-zero scalar multiple of this vector would also work for a vector along the line. So another way that you might see this answer written a little bit cleaner, if I were going to write this answer, especially if I were going to type it somewhere, I don't like to type fractions, I might use a different vector that's a scalar multiple of this. If I multiply this vector through by 2, then I will get 2, 9, 5 for the components of the vector. Right? So I'm just using a different vector that's parallel to this vector for my vector along the line. And then I still need a point on the line. So I'm going to still use my point 0, -6, -6. I'm not multiplying those by anything. Again, you're just really having to think through the geometry here, a point and a vector. If you multiply a point by some scalar, you've changed the location of that point, and that's not what we want to do here. But if you multiply a vector by a scalar, you're really just changing the length of that vector. The direction is still the same. So I might write my answer like this. Depending on how you do the problem, the algebra that you choose to do, your answer might look really different from each other. But there are a couple things that you should always see that would be ways to check. Whatever vector I have for my vector along my line, your vector should be parallel to that vector. It might be in the opposite direction, but it should be parallel to that vector. So our two vectors should be scalar multiples of each other. We might have different points that are on the intersection of the two planes, but either of the points, if you check those, whatever point you might have, if you check it, it should make both equations true, so that would verify that that is a point on both planes. So depending on the algebra that you choose to do, your answers can look very different, but you should be able to check those. And again, I really just did this kind of using algebraic techniques and thinking about solving systems of equations. Our textbook does something with cross products of vectors, which is okay too. I find that a lot of times students can't remember how to do that later. But either way that you want to do that, you should end up with an equation of a line of intersection of those planes.